Okay, so now it's recording. Now it's recording, and I do that. And why are you still here? Oh, okay, maybe I'll leave that there. Okay, okay, now I'm set. All right. So, uh, what's the darn date? Okay, it's 04/07/21. And the cool thing that we're going to talk about today is that we're going to actually write down some equations for how lasers work, and these equations will be true for all the different kinds of lasers. Every kind of laser that you can think about can be divided into, they are either three-level atom um, model, every laser. So every laser um, can be modeled as either a three-level atom model laser or a four-level atom model. Okay, and then you can have more. You can have a five-level or something, but these are the main ones. And you'll notice that there is no two-level, because it turns out that the two-level atom is the simplest atom. So I'm going to write that down here. That note two-level atom, where you have a ground state and an excited state, and this is the simplest model for an atom, but not for a laser. For an atom, but um, uh, it's impossible to make a laser. I guess laser width. Okay, so we'll see why, and it has to do. I mean, if you understand Boltzmann's principle, Boltzmann law of how energy is distributed well enough, if you understand that, then you'll also know why you can't do this with a two-level atom. And so the answer in short has to do with you can never get gain from a two-level atom. In any case, so we're going to see that you can either have a three-level atom or a four-level atom, and the equations that we write down are the same. And at that point, you know what? You are a fully trained optical engineer. You can go and work in industry. You know all the theory that a laser engineer knows. That's what I meant, a fully trained laser engineer. Laser engineers only know the differential equations that go with the three-level and the four-level atom, and those are extremely simple equations. So our goal is to derive, these are called rate equations. Rate equations for laser models. And what happens is that these rate equations, they tell you, they're very simple, first of all. In fact, Wolfgang Pauli, the guy who did Pauli's exclusion principle, he once said that rate equations, and he was the first one to write out rate equations for light atom interaction back in the 20s. And he said that they're so easy that even your grandmother can write them down, and stuff like that. So they're very easy. Now, of course, it would have to be a pretty rocking grandma who would know all this, but they are very simple, and you'll see why. Okay, so our goal is to derive these rate equations, and then what it will do is introduce you to ideas such as pump threshold and gain. Now, we've talked about gain, but now you'll have like quantitative, a quantitative picture of terms like this. Okay, so quantitative model. Okay, so let's start with this. And so this first module that I'm talking about is, or my goal here is simply to introduce you to these two terms. Okay, so my sub goal, I suppose, so that's my grand goal. But first, let's talk about these terms. So introduction. Let me write a little bigger, maybe. Introduction to this and this, okay, via a cartoon model, okay, for the laser. So what I'm going to do is, but it's a cartoon model with numbers and stuff. So, you know, so what we're going to do is, let's first, so here's the cartoon. Okay, the laser with the two mirrors, and there's the gain medium inside, right, like that. And what we're going to do is we're going to denote the photons inside the cavity, the intracavity photons, by Q. Okay, so as in there's Q number of photons inside the cavity. So this is the denote the number of photons actually inside the cavity by Q, and the number of atoms inside the cavity by denote the number of atoms, and let's be a little careful, in the excited state, because they are the ones that in excited state inside the cavity by little n. Okay. Did Andy get his his microphone to work? Maybe not. Well, but he'll see the words appear, I suppose. So we're okay. All right. So this is what we're going to go with, and we're going to actually, now let's try and write a differential equation for, because clearly you want this to grow, right? I mean, you want the number of photons inside the cavity to grow. So it's worth trying to write an equation for this, okay? And you can ask yourself then that, okay, so what makes Q go up? And what will make Q go up is, of course, Q goes up because of stimulated emission. Stimulated emission will make Q go up, and stimulated emission is proportional to little n, right? So if you want to increase the number of atoms in the excited state, which will make stimulated emission go up, which will then make Q go up. So that's one thing. And then the other thing is that what makes Q go down? What makes Q go down is, the first thing is that losses will make, we call them losses, but not all loss is bad. You can have some desirable loss also, meaning good loss, for example, is when you make the output coupler leaky, right? So you have losses, and then there is the desirable loss, which is the leaky output coupler. And then the undesirable, there are many undesirable things that can happen. You can have defects in the mirrors, okay? And so what I've written down here is that, you could have absorption in the coating of the mirror, absorption or scattering. Scattering happens when you have scratches and digs in your optical surface. So absorption or scattering in mirrors. I started out writing big, but then I'm sort of running into everything. Okay, so these are the things that make Q go up and Q go down. So if I'm writing an equation for the rate of change of the intracavity photon number, then I would have a plus associated with the stimulated emission going on, and so this thing here, how would I write that? This would be um, proportional to the number of atoms in the excited state, and you know these number of atoms in the excited state are going to emit um, more intracavity photons, and so the more of these two that you have, they will cause a positive change, an increase in the number of Q, and so it's kind of a circular thing that the more Q you have, the more atoms in the excited state, and so therefore this is a positive effect. Um, but we also need to, this is more of a proportionality argument, right? That this is proportional to that. What I need to do to make it an equality is there's a constant that I need to put in. And this constant is actually called the gain coefficient. Meaning that how efficient are you? Yeah, it's good that you have more intracavity photons and you have more atoms in the excited state, but how many of them are actually able to make the number of intracavity photons go up? And that's reflected in how efficient, what's the gain. So this is the constant right there. It's called the gain coefficient. And then what about the losses? So the losses I will show with a negative sign. And the losses, again, there are the how much will leak out through the output coupler. Well, the more photons you have inside the cavity, the more they will leak out. So that's one thing. And also, the more photons you have inside the cavity, the more you will lose through absorption or scattering at the mirror. So the proportionality, for the loss is simply, the more you have inside the cavity, the more you will lose. So you notice, but then of course, that's a proportionality relation. What about the equality? So I have to put in another constant, okay? And this is called the loss rate. It has to be a rate because, on the left-hand side, the dimensions are change of Q with time. And then here, this is just Q, which is the intracavity photon number. So I need to multiply it by a rate. And that also tells you that gain coefficient times the number of excited state atoms, that also is a rate, right? A times N is a rate. The B is a rate. And so this is my, that's the loss term, there's the gain term, and this is my differential equation for the intracavity photon number. Note how general this is. It's a very generic sort of equation. Okay, it applies to just about any laser you can think of. All right, and so both of these together are it's just the rate of loss of photons. And this, of course, is the rate of gain of photons. All right. Let me write a similar equation. So that's one equation. Let me write a similar equation for the atoms in the excited state. Okay. And then I'll stop. These are the equations. We'll solve them in the next. I'll give everyone a break. So what about this? Let's look at let's look at what causes, if you have some atoms in the excited state, what will cause a loss of the atoms in the excited state? Well, you can have spontaneous emission. So the spontaneous emission, you know, I could, if the spontaneous emission rate is, let's denote it as with an F, and then I need to multiply it by n. So then this would be the spontaneous emission rate. Okay, so this is a loss rate due to spontaneous emission. Okay, so that's one. You also have loss due to stimulated emission. I mean, you're in the excited state and you fall back down. Okay, and so there's a stimulated emission rate also. And the stimulated emission rate would again be proportional to the number of atoms in the excited state. It would also be proportional to how many of these atoms in the excited state are being illuminated by photons. So you see, it depends on the product of those, right? Because for stimulated emission, you need an excited state atom to actually see another photon. So it's the product of those two. And but again, this is a proportionality. What's the constant that makes it that then makes it okay to put it into an equation? Well, it's this very same gain coefficient, meaning that if I multiply it by A, then this would be, and this A and this A are the same, then this would be the loss rate due to stimulated emission. So the same, I mean, that's just saying that, you know, your the absorption rate of photons for stimulated emission is the same as the loss rate due to the stimulated emission. So absorption up and then emission down due to stimulated emission, those are the same rates. Okay. Now I'm seeing two loss terms. Where's the gain? And so meaning like I have to replenish this somehow. All the atoms in the excited state would just decay down due to spontaneous emission or due to stimulated emission, but how to replenish it back? And so that's why there's always some source, like a heat source, which keeps the whole medium really hot and keeps putting atoms up into the excited state, or there's another pump laser, okay, which will pump atoms back into the excited state. And so that we're going to just represent very generically and simply by plus P, where this is the pump rate. Pump rate to replenish atoms in excited state. I've been yapping for 19 minutes, so I do want to stop. These equations are extremely simple, and just by examining them under extremely simple conditions, you know, like for example, we might say, well, tell me what the steady state solution is. Okay? And the steady state solution is very simple to solve for. And by solving for the steady state, we will actually learn already what these two terms mean, that there is something called a pump threshold, there is something called a gain. So I'm going to actually now stop recording, allow everyone to rush to, you know, get some beverages or something to replenish themselves, because I see that if I were to write an equation for you, there's a lot of loss terms at this point, loss of brain cells and loss of, like, you know, because of Samir rambling on and on. So I'll let you go and take care of the plus P thing. And literally it's a P break. Okay, so let me just stop recording. and